So next talk would be, again, all testbed related open source. So I wanted to make sure how we are started from what's happening in the standard, then getting into actual testbed. So next talk will be an overview of Virginia Tech CCI exit testbed, North American OTIC in Washington, DC metro area. It will be given by Dr. Mayukh Choudhury. He's a postdoc research associate with Virginia Tech. So I know Mayukh for a few years when he was doing his PhD in IIT Delhi, but he also had experience with 6G Lab, Samsung Research Development Institute in Bangalore. He got his PhD in Delhi in 2022 and master's from IIT Partner. He also had some internship at TCS Innovation Lab. So with that, I'd like to invite Mayukh for a 20-minute talk on testbed, and after that, we'll have IEEE 5G 6 innovation testbed. So let me open your slide. Which one is slide? This one, right? Okay, let me just share. Share it. Okay. Oops, what is up? Screen, what? Let's try that. Why didn't it happen? My file open. Yeah, so your file was open. You can try to open this one. Maybe this close. Okay, let me just go to the. You can close the other PDF files. Not PDF. Is that the problem? Maybe. Or you can just do. If you just do you want the thing, you can just run it like that. Oops, sorry. Yeah, no, that's different, right? Right. Stop sharing. Last time, losing time. Can close that. Yeah. How do I close it? Yeah, go this. No, it's trying to. Okay. Okay. So okay, you can go to that. No, you haven't opened my. Let's close it. Yeah. Let's try to finish it. Let's try again. If it doesn't give a problem, we can just do it the way. No, here. What's up? You clicked on that. You close this. Oh, okay. Share. Just this one. Yeah. I think no, this comes, but then what all of a sudden it becomes. When I do large view. Okay. Okay. Like this.
Thank you, Ashutosh, for the introduction and also for inviting me to this talk and to IEEE as well. So I'm going to give a brief overview about the Virginia Tech CCI exit testbed that has recently been approved as an OTIC center, and that is very close to Washington, DC metro area. So let me give an overview of the agenda. So I'll talk in brief about the CCI and then how we have built this testbed as the OTIC platform. And then two primary components of the testbed. So the first one is the indoor and the second one is the outdoor testbed. And then I'll talk about few research we have done in this testbed. All right, so what is Commonwealth Cyber Initiative? So it is an initiative from the government of Virginia, primarily to build the workforce around the cybersecurity or cyber physical systems in general. So it's a consortium of 40+ institutions and 300+ researchers So we leverage industry, academia, and government collaboration. On the research side, we focus primarily on wireless communication, cybersecurity, autonomous, and intelligence systems. So the ORAN compliant exit testbed that I am going to talk about is part of this CCI. So maybe I'll skip this. So these are some of the community engagements of CCI exit testbed. Of course, we are part of ORAN Alliance since 2021. We are also part of NextG Alliance, which is primarily led by Virginia Tech Applied Research Corporation, or VTARC. We are also part of ONF and National Spectrum Consortium. We work very closely with Software Radio Systems, or SRS. We have started working with them to build up the CCI SRS lab in North America. All right, so these are the current 6 labs which have been converted to OTIC centers. So we had speakers from Kyrio, from Cable Labs, Colorado, and also from Northeastern University. So our Virginia Tech CCI exit testbed has been part of this OTIC list. And we have 2 components. One is the indoor testbed that is very close to Washington, DC metro area. So these are the different sites that are part of this OTIC center. So we have the North of Virginia node where we are present, and also George Mason University is there. We have the Southwest Virginia node where Blacksburg main campus of Virginia Tech is taking the lead. And we have the Coastal Virginia node where we have Old Dominion University taking the lead. So also we have 3 industrial partners, namely AT&T, Verizon, and Dish, who are co-hosting with us. And we have the academic partners, as I already mentioned. So these are the 2 components of the CCI exit testbed. The first one is the radio grid network. That is the indoor component of the testbed that is located in Arlington, Virginia. And the second one is the CBRS-based private network that we are building outdoor in the Virginia Tech's main campus in Blacksburg, that is in Montgomery County. So these are some of the capabilities of the testbed and the goals. Like we primarily focus on real-world experiments, end-to-end testing, both in lab and on the field. And we focus on the interoperability as well. So we do a lot of design, development, and deployment of cloud-native softwares, which are both software-defined and open source. We are definitely open to and leverage a partnership with both US and non-US universities, industry, and governments. So we allow the users to run experiments, measurements, and to collect the data across all these 4 testbeds in the OTIC site by remotely logging to the terminals through VPN and SSH. So for the indoor experiments, we use FCC experimental license. And as a OTIC center, we are currently focusing on these 3 testing scenario: conformance testing, interoperability testing, and performance testing. So I'll talk about in detail about the indoor testbed that we have. So this is the visual of the radio network platform, the radio grid. That is a combination of 72 software-defined radios, which are basically mix and match of X310, X10, X410, N310, B210, and B205 mini. So these are completely end-to-end ORAN based. So all these USRP nodes are connected through patch panel and the optical fibers to the backend servers. So on those servers, the users can remotely instantiate VMs, and they can place their microservices or their containers on them, and they can control these radio nodes through those scripts, and they can run their experiments. So this is the system architecture of the radio network that we have. As I showed, that these are 72 USRP nodes, which are distributed in 9 rows with 8 USRPs each. We also have power distribution units, which are PDUs, which give control to the users, the remote users, to turn on or turn off the terminals or the USRPs. We also use octoclock for the synchronization between different nodes. So all these USRPs, as I was telling, are connected through switches or the software-defined networking or transport network to the backend servers. Let me talk about the open source softwares we are currently using. So as I was telling, it is completely end-to-end ORAN compliant, and also we connect this RAN network to the core as well. So on the core side, we instantiate virtual networking functions of 5G using open source softwares like Open5GS or Pre5GC. On the RAN side, starting from the AIML framework, so I'll talk about it in detail. So we have used open source softwares like ClearML, which are MLOps software for the AIML framework. And then we use ORAN Alliance non-real-time RIG and near real-time RIG. And on the RAN side, we primarily work with SRS Fan, but we have also started working with OAI as well. So our complete cloud native platform or the cloud deployment is based on OpenStack, which is an open source software. That's pretty much it. Okay. So I'll talk in detail about the AIML framework integration. I think the stage has been very well set up by the previous two speakers, Shankar and Dilip. So I'll talk about it. Okay, so this is the current status of the AIML framework integration to the CCI XG testbed. So we have the non-real-time rig where we are placing the inference host, and we have a separate training host that is basically the AIML framework. So in the training host, we are running a ClearML's agent, which is my training agent, and that generates the trained model out of the data that we feed it with, and then the saved model. I mean, the model is saved in a database from where we update the model to the inference host. So inside the inference host, we have ML inference RAP, and there is a data lake where the overall data from the RAN is collected and stored. From that data lake, we used an assist RAP. So this is something Shankar was also pointing to, like when you want to use some inference RAP, the input has to be compatible with it. For example, if you are storing the whole data in the data lake, from that, let's say you are using supervised learning. So you have to convert that data to the required features that will be fed to the inference. So this assist RAP does that job. So in case of supervised learning, it will convert your input data to features, or in case of, let's say, reinforcement learning, so it will convert the input data to states. So that is the job of the assist RAP. So then we have used for this current implementation Kafka to implement both A1 and O1. It offers you the options of REST APIs as well as gRPC. On the RAN side, currently in this implementation, we have used SRS RAN. But of course, as I told that we also work with OAI as well. So please note here that as of now, the inference is taking place only in the non-real-time rig. Whatever inference the non-real-time rig is getting, that is passed to the near real-time rig, and that has an actor XR that only implements that action. So the inference is not taken in a near real-time rig as of now in this setup. But we are working towards that. I'll talk about that. So this is a demonstration of the AIML framework end-to-end AIML control loop for ORAN that we demonstrated in Mobile World Congress last year in Las Vegas, and also we showcased this in Infocom demo New York this year. So we used some application like RAN slicing, where we showed that whenever there are regular users, they are given some resources, but as soon as some priority user comes in, for example, first responder, then some of the resources are automatically transferred to that user so that their quality of service is adhered to. So this is an end-to-end ecosystem where we have non-real-time rig, near real-time rig. We have built these dashboards to showcase this, and we have used both software UVs based on SDRs as well as COTS UVs. So this is an ongoing work that we are doing very closely with Samsung, primarily Samsung Research Bangalore in India. There is some MOU taking place between Virginia Tech and Samsung regarding this. So we are trying to, because you know that Samsung is taking the lead in the AIML framework in the ORAN Alliance or ORAN software community. So we are working very closely with them. So in this deployment, the idea is like the inference will be in both near real-time rig and non-real-time rig. So in the near real-time rig, there will be an inference platform, which will be based on Kserve, which is also open source. And on the non-real-time rig as well, there will be one inference host, which will be based on Kserve as well. But the difference is like the AI inference host platform that is in the non-real-time rig, that will host ML RAP, and the one in the AI inference host in the near real-time rig will have ML XAP. So then the training is being done in this AI training host platform, which has a training platform service, then that is based on open source software called Kubeflow. And for the data lake, we are going to use InfluxDB, which is an open source software. Yeah, that's it. So now let me talk in brief about the outdoor testbed that is built for a CBRS-based private network that we are building in Blacksburg campus. So before I move into this, let me talk in brief about what is CBRS. So CBRS is very much US-specific band that has been offered by FCC for a hierarchical user. Like there is in this grid, there are 3 levels of users. The top most is the incumbent, which is the highest priority. Those are primarily Navy radars or US military or satellite services. The next in line is the priority access license, which has to be bought through auction. You have to pay for that. And the third one is the general authorized users, which are free users, but those are like shared basis, first come, first serve basis. Whenever the other users are not there, they can use that. So the background of this testbed is like the Virginia Tech Foundation, they acquired 4 bands of 10 megahertz in the FCC auction in 2020, when FCC gave these CBRS bands. So we got 4 chunks around these 2 counties, Craig County and Montgomery County. So around from 3.61 gigahertz to 3.65 gigahertz we got. And the concept of CBRS has moved from previous static exclusion zones to dynamic protection areas. Like previously it was like whenever incumbent is there, around that area you cannot transmit. But currently they are moving to more dynamic scenario where you can offer some flexibility in this. Like there will be a protection area, but it will be dynamic with time, not quite static. Also, the use case we are going to take up in this CBRS private network is very interesting. So inside the Blacksburg campus, we have something called Straubel's Creek. That is a creek that is flowing inside the campus, but that gets flooded during the rainy season. So the community who lives around that area gets affected by that. So we have collaborated with Biological Science Engineering Department and the Agricultural and Life Sciences Department, who will be deploying some sensors there, which will do the flood monitoring. Now, these flood monitoring sensors have to be connected to this to some network, right? So for that, they are already deploying a production grade network there, which will have all commercial equipments and commercial softwares. So we are planning to co-locate our experimental setup, which is also CBRS based, with that production grade network, so that we can interplay with them, we can exchange information, and we can also generate data sets for the both experimental and the real network. It will have access to a lot of real data sets. So this shows the area of coverage, like where we have got the license. So this is the deployment area. This is primarily a 1.5-mile corridor inside the Virginia Tech campus. It also includes the drone park as well. So we also plan to involve the drones as well in the experiments. Yeah, I'll show the visuals. So these are the visuals of the actual CBRS radio sites. So the first 2 are some departments. The first one is the agricultural building. Second one is Han Hall North, which holds the physics and the chemistry department. And the third one is very interesting. So it's a animal husbandry barn with so it has a lot of cows around, and it has some farmlands around. So we have deployed this in strategical locations, which are very unique in nature. So how we are going to use ORAN in this ecosystem? So the central role in this CBRS-based spectrum access is taken by Spectrum Access System, which is called SAS. Now we have worked with commercial SAS like Google SAS and Federated Wireless SAS, but the problem is they do not talk with CBRS-based SDRs. Now, for us, as Shankar was mentioning, like when you do experiments in universities, you have to focus on open source softwares. And that's why you need systems like SDR-based CBSDs. Now, how do we connect that to a SAS? So for that, Virginia Tech researchers have developed open source SAS called Open SAS, and we have integrated our CBRS-based SDRs, SDR-based CBSDs to that Open SAS. So this is a picture of the demonstration that we gave in IEEE Infocom demo on the integration of Open SAS with the CBRS, the SDR-based CBRS-based session. So I'm just glancing through this, like this is another work that we are currently doing, like some of the functionalities which are done as part of the SAS involve some intelligence. One of them is the incumbent detection. So the idea of having the SAS is to protect the incumbents. But for that, you have to detect the incumbent first, right? So this is one machine learning algorithm we have used, and we have published this, that is accepted already. It will be presented in the ACM WinTech this year in Madrid. So that has showcased AIML-based incumbent detection in a CBRS-based experimental network with Open SAS. So this is some of the ongoing work that we are doing. The first one is very interesting, like how we do spectrum sharing in case of radio astronomy. So this work is in collaboration with University of Colorado Boulder and University of California, Berkeley, and also with Google as well. So there we went to this Hat Creek Radio Observatory that is in California. So that is a radio astronomy site. That means they use radio frequency to do their observations. astronomical observations. So whenever they are trying to do that, at that point of time, they are the incumbent. So they are the highest priority. So if at that point of time, if there is some CBSD around, so they can create some interference, but that is not desired. So the job of open SAS, we have deployed open SAS, we have enhanced its functionality to work is this kind of scenario where it will do spectrum sharing for radio astronomy sites. So it will try to reduce the interference for these radio astronomy sites. So another work we're currently doing is like how we can use ORAN for dynamic spectrum access. This is in very nascent state. I will not talk in detail about it. Like how those intelligence can be built as part of the near real-time RIC, and how we can create XApps for all those individual functions like interference evaluation and interference detection and spectrum monitoring, let's say. And so you know that RF sensing is required in these kind of scenarios, which are called environmental sensing capabilities or ESC. Now, in this scenario, the radio nodes or the radio units themselves can act as the ESC nodes or the RF sensors. So this is something we are currently exploring. So yeah, there's some ongoing works. So I'd like to conclude by inviting you all to join us in the first ever SRS Fan Workshop that we are going to hold in collaboration with SRS Lab. This will be taking place in October 23rd and 24th in the very building that we are based in, Virginia Tech Research Center, Arlington, very close to Washington, DC. Please join us. So this is the link to go to and register for that. And we'll hope to have all of you to join us and have a lot of keynotes and real hands-on experience of the software communities for the ORAN. Thank you very much.